Hi, it's Paul with another binomial model simulation in R, similar to ones you've already seen, except that this time it's going to lead almost directly to the Black-Scholes option pricing formula. So let's put in the parameters. We have to specify the price of the underlying security at time 0, $50. Maturity date, 4 years. The number of steps. As long as this is large enough, the central limit theorem will apply, and you might want to try on your own changing this 300 to 600 or 1200. You'll see it makes very little difference. And finally, a measure of the volatility of the stock, sigma, and the meaning of sigma is that over a time interval t, the variance of the exponent is sigma squared times t. I'm going to set the interest rate equal to 0, and then we don't need to introduce any drift except what we need to make the price into a martingale, and we already know what that is. The mu we need is minus sigma squared over 2. Okay, now you've seen this before. We'll store little n plus 1 prices. The step length, of course, is going to be the total length of time till maturity divided by the number of steps. And the standard deviation in one step, that's sigma times delta x. And we know that delta x squared equals delta t. So once we have chosen the step length delta t, we take the square root of that multiplied by sigma. That gives the amount of an up or down step in the exponent. I'm going to set range equal to 2.5. That just means I will display without going off screen final prices that are up to 250% or as low as 40% of the initial price. And I'll set up a blank plot using the rest of my screen. Okay, you've seen this simulation done before. All I did was start with the price on day 0, and for each step I took the price and what I'm doing here is instead of a fixed step up or step down, I'm just using a normal distribution that has the same expectation, namely 0, and the same variance as our binomial distribution. Store the prices, plot them, and you can see it looks much the same as our pure binomial model from last time. And remarkably, even though I replaced the finite steps by a continuously distributed random variable, the strange wiggliness and these long strings of up steps and down steps persist. Let's confirm that we still got a martingale. We'll now generate 10,000 final prices and do exactly the same thing, storing the final price. And now you can see I've done it all in one step. I'm just taking a normal distribution where I have multiplied the variance by the amount needed to go from the square root of the length of one step to the full time t. So I'm now using the normal approximation to the limit of a binomial distribution. If I've done things right, the mean of those 10,000 final prices should be close to 50. It is. If I've done things right, I should find that the logarithm of the change should have a slightly negative mean, but I know exactly what that is. It is mu times t, and furthermore, I know the variance of the logarithm of the change in price. It should be very close to sigma squared times t. Now let's look at the distribution of the prices. Here's a histogram of the final prices. It's got the now familiar tail to the right. As with the binomial model last time, the median price is a bit less than the mean price, and there are some fairly extreme outliers. The price could go down from $50 to $9.59, or it could scoot all the way up to $236. If the random walk contributes absolutely nothing to the price, then the price will evolve to the initial price times the exponential of mu times t. That gives us back our median price of $46. Now let's think in terms of options. We'll take a strike price of 60. As you saw in a previous script, I can calculate the probability that the option's in the money by just taking the mean of the Boolean array whose entries are 1 if the final price is greater than k, 0 otherwise, and I find about 25% probability for the option to be in the money. How big an exponent do I need to get that? Well, the exponent I need is, of course, the logarithm of the ratio of the strike price to the initial price. That's about 0.18. And if I calculate the probability that a normal distribution has that value or greater, I get back about 25%. Now, I can predict the entire distribution of prices. This is a little bit tricky, so watch carefully. I'm going to initiate a vector of simulated prices by putting in the price x0, and then I'm going to keep appending more and more prices to this vector. And what I'm going to do is break up the range of values for the exponent in the formula. Final price is initial price times the exponent of some number. I'll break it up into 1600 intervals that range from -4 times sigma times the square root of t to +4 times sigma times the square root of t. And that means an individual step, if I'm going to have 1600 of them, has to be sigma times the square root of t over 200. Now I'll just step through each of those 1600 intervals, and what I will do is calculate the price if I have a value in the middle of that interval. That is I steps plus another half step. I will calculate the probability of being in that interval by asking for the probability that we exceed I plus 1 steps and subtract off the probability for exceeding I steps. And for each of these intervals, I will append to my growing vector of prices a repetition of the current price by the rounded value of the expected number of prices that will fall in that interval. Looks a bit far-fetched, but if I overlay a histogram of that on the previous histogram, the two histograms match almost perfectly. And the mean value of these prices is very close to 50. Okay, now you see we can predict the probability of any final price, and therefore we can easily calculate the fair price of a call option. That's the role of the Black-Scholes formula. Okay, all I have to do is take the final price minus the strike price and multiply by 1 if and only if the final price exceeds the strike price. And when I do that, I get a value of 4.51. Don't try to read this whole formula, but this is the Black-Scholes formula. And for the moment, what matters is it computes almost exactly the same number. Same thing works with any strike price. We could have a strike price of 30. Now the stock can decline quite a bit and the option will still be in the money. And what we discover is the value of this option is substantially greater. It's about $20.81. And we can check this with the Black-Scholes formula. But since we're going to be doing this a lot, and you'll want to do it in workshop problems and homework problems, what I've done is to design a function named Black-Scholes that takes price on day one, strike price, time till maturity, interest rate, and volatility, and calculates the fair market value of the option. Here, these variable names are ones that I've already been using, but since they're inside a function definition, they're in a different namespace. Don't let that worry you if you're not into the complications of namespaces. All I have to do is plug in the values we've been using, and I get back my $20.73. Now there's one more way of doing this, and this will actually lead into the derivation of the Black-Scholes formula. Let's define a variable that will end up being the value of the call option, initialize it to 0, and another one that will end up being the probability that the call option is in the money. And what I'm going to do is a Lebesgue style integral. I'm going to break up the codomain into short intervals of price to price plus 1. That's a small piece of the codomain, and for each $1 subdivision of the codomain, I will use the normal distribution to estimate the probability of getting an exponent that leads to a price that falls in that range, and then I will just sum up value of the option times probability of getting that value. So here goes. My prices start at K because for a price less than K, the option isn't in the money. I have to calculate two logarithms. The logarithm of the ratio of the price to the initial price minus mu times t to take the drift into account that I put in. And then a similar quantity which I've called log 2 where I use the price plus $1. The probability that the price is in that range is given by the probability that the normally distributed random variable with a variance of sigma times the square root of the time till maturity exceeds the larger of those two logarithms minus the probability that exceeds the smaller of those two logarithms. That's the probability that the price is in between the value price and the value price plus 1. So all I do is add on to value this probability times the price plus 0.5 to be in the middle minus k. That's the value of the call option if the price is in the middle of the range. And what have I got? When I sum up all the probabilities, I find an 85% probability for the option to be in the money. And I have replicated that value of $20 and change of the fair market value of the option. Now all I have to do, if I want to derive the Black-Scholes formula, is repeat this calculation, only except instead of trying to approximate the value of the Lebesgue integral by breaking it up into a finite number of bins, I will instead calculate it analytically.